All right. Good morning, everybody. My name is Jenny Montblanc, and on behalf of the Great Basin Fire Science Exchange and our partners, I would like to welcome you to this webinar titled Unmanned Aircraft System Drone, Noxious Weeds and Fuel Load Program, presented by Dan Wobbe from Mazer Consulting and Chris Wilson from Wilson Herbicide Spraying. All right, I have to state a disclaimer up front that hosting this webinar does not constitute an endorsement by the Great Basin Fire Science Exchange of Wilson Herbicide Spraying or Mazer Consulting. It's simply an informative webinar to see what these new technologies can do. Before I introduce our speakers, I will go over some webinar details. If you have questions or comments for the speakers or me, please type them into the questions window of your control panel that's located at the top right of your screen at any time during the webinar. I will field your questions for the speakers after the webinar presentation, so you're welcome to type a test message or test your audio at any time during the webinar. If you're having problems with your audio, please open your audio window and check your audio selections. Now I would like to introduce our presenters. Dan Wobbe is a professional land surveyor and is the Northwest Geospatial Manager with Mazer Consulting and recent FAA 107 pilot. Dan is based in Redmond, Oregon, and has over 28 years of experience in all facets of surveying, including remote sensing, mobile and terrestrial LiDAR around the world. Chris Wilson is the Vice President of Wilson Herbicide Spraying, LLC, based in Adel, Oregon. Chris is a licensed commercial pesticide applicator, and he has several achievement awards in forestry training and a forward vision for advanced environmentally friendly solutions. Welcome, Dan and Chris, and thank you for presenting today.
Thanks, Jenny. Hi, I'm Dan Wobbe. Yes, with Mazer Consulting. Sorry, Chris. I just got a message on my screen, Jenny.
Yeah,
Can you still see my screen?
I just made you the presenter.
Okay, perfect. Well, thank you all for attending this presentation on UAS drone resource management, fuel load, and noxious weed control program. So a little bit about who we are and how we got here. Chris Wilson was a good friend of mine. Well, still is. And we were talking about a better way to solve the noxious weed and fuel load problems that are out there. So Wilson Herbicides and Mazer Consulting came together in a teaming agreement, and this is where we are. Wilson Herbicide Spraying, they're a woman-owned, hub-zone, small business located in Adel, Oregon, which is just about 13 miles north of the Nevada-California border, where it intersects Oregon. Mazer Consulting is a 600-person geospatial firm. We've been in business since 1984 and been leading the way in remote sensing, LiDAR, and surveying technologies. So Chris, this is 3.
So what we're working with is what we can do to improve the existing workflow, and these are the concerns we have with the existing workflow. We see that right now the current mapping we use is based on low resolution satellite or fixed wing high altitude sensors. So the pixel size for looking for plants is too large to be accurate, or especially for plant outbreaks. We see field and spray activities that lack precision and can result in unwanted consequences of overspray. They're labor intensive, and they have a high environmental and safety risk as far as for the helicopter having drift issues or for the workers themselves being exposed. We also see environmental challenges. If we disturb the ground with ATVs and trucks and tractors, that type of thing, we break the ground and the crust of the ground and make an area for these noxious weeds to take hold and to become an intrusion, ruin habitat, start fires, reduce the fire cycle like you guys see on a daily basis. Dan, can you move us to the next screen? So here are the goals of our revised workflow. We want to accurately be able to identify the weeds. We're going to use global positioning, spray location control. We're going to control the amount that we spray and where we spray it. We're also going to have hard boundaries so that if we have a lake or certain habitat that we don't want to have overspray, we can set those so that there's no way for the drone to spray outside those areas. They're going to be geo-fenced. And then everything we'll do is repeatable, quantifiable. We can fly over repeatedly later and see and verify what we've done. We're going to use a GIS database to show where these plant species are. So if you look at the picture in the top right, this was a knapweed breakout, and you can see the green is the noxious weed and the other stuff is native habitat. And with that, rather than ride through it and disturb it, we'd like to spray just the locations from above and have a more accurate and precise and less disturbing process. Dan, are you ready to move on?
I am. Having a little bit of trouble here with it moving forward, though. Okay, so why now? Why hasn't this process worked in the past? And it basically comes down to technology. The technology advancements haven't been there, and they actually haven't been there till probably 6 or 8 months ago. If you look up in the upper left-hand corner picture in the corner of the tan background, that's a hyperspectral sensor that you typically see on a manned aircraft, and they're super heavy and bulky, and couldn't fit those on a UAS or a drone. So you see the new sensor to the right. It's actually about the size of 4 golf balls, and it weighs only a couple ounces. And here again, that sensor has been out for a short period of time. The LiDAR sensor, same thing on the bottom left-hand corner. That LiDAR sensor, it's got a computer rack, storage systems, an IMU, which is an inertial measurement unit, the laser, the cameras, the scanner. The whole system was several hundred pounds, and again, just too big to deploy on a unmanned aerial system. So you see the new LiDAR sensor. The one we use is a Regal sensor, Bucks, and it weighs a couple pounds, and which allows us to finally deploy LiDAR on unmanned missions. Another big change has happened in the recent past, and is continuing to change, is software automation. The automation software, they've claimed for years that it does everything, it extracts everything that you need, and it hasn't really worked as well as everybody has claimed it to. And that software is getting better and better every day. And UAS technologies, they're every day they're changing. If I miss a weekend reading news on UAS, I feel like I'm a month behind. Far as flight dynamics, endurance, capabilities, battery life is a big one, and motor efficiency. And flight mission planning, it's better and better. Even the GPS sensors on the UAS are 100 times better than they were just a couple years ago, which allows us to produce survey grade data from a UAS without targets on the ground. And automated spray control. I mean, that's something that's brand new as well, and being actually developed by other vendors as we speak. Looks like we might just drag out this presentation just in between slides. Sorry about this.
Is it just a delay?
No, it's not moving on my end.
Huh. Interesting.
Okay, I just had to push the button 30 or 40 times for it to work. So LiDAR, what it simply means stands for light detection and ranging. light pulses are emitted from the laser scanner that's on the craft. It scans about 500,000 points a second, which is a lot of data. Each point has an X, Y, and Z value, and RGB, red, blue, green value associated with that point. Each laser measurement has up to 7 returns. It actually, they state it can get to 10 returns per pulse, but we typically see 7 returns. The craft uses GPS on board and also uses a base station on the ground, so we can post-process the flight, including the IMU, which is the inertial measurement unit, which calculates the yaw, pitch, and roll. That IMU is similar to systems put on self-guided missiles. Now I'm going to click the button 30 times. Oh, it worked. So LiDAR, basically how it works, you see in the upper left-hand corner, we have our UAV craft, and this shows that red line, that laser coming down from the sensor head. As a sensor breaks through the tree branch, as it hits a tree branch, it'll split, and part of that laser will go down and hit the next branch, and that laser gets smaller and smaller and smaller, and finally what it'll do is eventually touch the ground. And not all laser pulses will hit the ground, but when we're getting 1,000 points per square meter, there's plenty of data that is hitting the ground, and a lot of data on trees and shrubs above ground. So Hyperspectral, our sensor guy, who usually gives this presentation, is actually in the UK right now, picking up another sensor. He could explain this at a much higher level than I can. I'm going to kind of break it down to a level that I understand. So basically, the way I look at this is you have a camera, a digital camera, let's say your cell phone. You go out and you take a picture, and you go in, you look at that picture afterwards, and you zoom in, you zoom in, you zoom in, and the farther you zoom in, you start seeing little squares. And each one of those little squares, when you look at it, is going to have one color associated with it. You zoom back out, all those colors blend together and to make your photo. So think of hyperspectral as each pixel that it's going to pick up. If we took that same picture with a hyperspectral camera, each one of those little pixels is going to have up to 270 bands of spectral information associated with it. Each plant species has a specific spectral value to it that's only to that certain species. So by having all this information, we can run this through programs and algorithms where I say, okay, go through the software and look for this particular spectral band, wherever it fell for that particular species of a plant. So hopefully that made sense to you guys. And this is just kind of want to show you a basic flight operation. This is actually what our pilots would see when they're operating a craft. We have all of our flights are autonomously flown. So if you see this black box around in the picture around the green lines and the squares and the blue triangles, that's actually a flight boundary. Our craft, if the pilot was manually flying this for some reason, had to take over controls, the craft would not cross that boundary. It'd fly right up to it and would not cross it. So I mean, that defines the boundary. We can also create those. I think Chris mentioned earlier that we can create these boxes inside for like waterways and whatnot for restricted areas to fly. Our craft also has sense and avoid technology. So flying out there, if something didn't get picked up on the pre-flight, a tree, a structure, whatever, our crafts have that technology to sense that. We also have terrain following. Let's say you have a sloped or piece of ground that's sloped 45 degrees, or maybe it's just up and down across, and you want to maintain, let's say, 10 feet AGL above ground level. Our crafts have the ability to follow the terrain and stay at that 10-foot elevation. Obviously have hover capabilities, and then on our spray control systems, we have Wind compensation. We compensate for rotor downwash, and again the geofencing for marking out areas of concern. Chris?
So here we are again to the workflow for noxious weed mitigation. We want to use this technology to identify using the aerial platform. We want to know the regions and the specific areas that we have these noxious weeds or pests. And then we're going to map those to a GIS platform so that we have the proper way to move forward for the drone to know where to spray and where not to spray, so that we're not spraying, say, the water in a particular area, but we could spray on both sides of it, or we could avoid sensitive crops or sensitive species. And then we want to use the UAS to autonomously spray those areas in a pre-designed flight mission for that. Then we're going to come back and monitor using this type of sensory information to tell us what we did, how well it worked out, and how successful we were. And then we can come back and spray either the areas we didn't do well in, or we can use those same flight plans later. Maybe we mapped this year and we want to come back next year and map at the right time of year. We'll have that information ahead of time so that we can quantify and repeat and keep coming back to have a successful process moving forward.
So identify. Here's an example of hyperspectral imagery. You can see in the bottom right-hand corner. It's been proven as an effective way of identifying noxious weeds and other plant species. There's been case studies for the BLM, for the Idaho State University. You can look in this picture, this image below, and you can see where we were able to go in through automated processes and extract locations of needlegrass, juniper, and Medusa head rye. If we combine LiDAR with this application, it does give you some advantages. Not only can we determine fuel load with the LiDAR, which you can't with hyperspectral, because hyperspectral is basically one-dimensional. And it also can define closely ground heights and slopes, especially if we're doing spot spraying. We need to be a couple feet off the ground. LiDAR would enhance that model. And then mapping, broad applications can be still mapped by helicopter. And this is a good example of where we're going with this, and using a combination of manned helicopter missions and UAS applications. This was a project we were looking at doing where it's a large chunk of land. It wasn't cost effective maybe to do the tens of thousands of acres with the UAS. Because of beyond line of flight restrictions. So we took a look at this and said, you know what, with the client, and said, you know what, they can broadcast spray with a helicopter all these other areas. There's no really areas of concern except when you get around the bodies of water in the wetlands. So we created this flight boundary, this area in yellow, which we're going to fly our craft, and it's going to go through there and do surgical spot spraying and minimizing chemicals and herbicides placed in around these wetlands. And Chris, you want to talk about the restoration after a fire? The use of mapping, yeah.
So a couple of the things we're looking at is, one, if we have areas that we know we have either noxious weed outbreaks or that we have sensitive native habitat, if we're pre-mapping in those areas before a fire, after the fire we know where we need to spray for the noxious weeds and where we need to leave the native habitat so that it has a better chance to come back and establish itself and have a chance to beat cheatgrass and Medusa head and these types of species in these areas. And for restoring after that fire, the value of that and what the cost of that fire restoration is, this would be a great tool for using in those areas.
Perfect. Okay, sorry, I'm having problems with my computer here. So I'll mitigate. Based on spray areas, we'll try this one more time. There we go. So on mitigate, based on spray areas, we'll evaluate the best tool to perform the spray application, as we mentioned before, either be traditional helicopter spraying systems or UAS based spray systems. We'll develop flight planning for spray areas and flight weather restrictions, define no spray boundaries around habited land areas, wetlands, waterways, wells, or whatever the case. We'll utilize mobile ArcGIS collector app in the field for planning and UAS spot spraying. So UAS mitigation technology, FAA 107 states that a UAS platform must not weigh over 55 pounds on takeoff. All of our crafts do meet that regulation. Our crafts are all autonomous flight controlled via GPS. They have spot and broadcast spraying abilities and a range of nozzle choices. And the spray flow on this particular craft is 0.9 to 2.4 liters per minute. Monitor. Flight missions are repeatable. As Chris mentioned, going back year after year after year is very doable. Being a professional land surveyor and very involved in geospatial work, all of our craft, all the missions that we fly are survey grade, so we can go back time after time after time again. Additional sensors flight for mapping to assess success, recording of chemical applications and environmental conditions, wind direction, speed, humidity, temperature, and those types of things, and field inspections. Chris, was this you?
Yes, Dan. So here we're coming back to the quantify part of this, that we can independently assess broad application, helicopter versus the targeted UAS type application. We have the GIS mapping record of the spray areas. We have GIS field mapping tools to facilitate field verification so people can walk out into the field and look at where we work to verify the work that we've actually done and see what we've done and see it, not just see what the drone tells us we've done. The geo-reference reporting a spray application and effectiveness so that we can go back to those areas, see how effective we were, record that, know what our plan is for the next year. If we need to change chemical or the time of the year, we'll have all of these tools and be much easier to use. The geo-reference lessons learned and recommendations for future mitigation, coming back to what do we want to do next year and the year after so that we can continually see an improvement and or at least hold our ground, but we don't want to see our problem get worse and worse every year, kind of like we do in some places now. And then data integration, that we'll work with the WETS and the NISMIS system. We'll upload all of this stuff to government databases where we can share this with all the agencies, BLM, Forest Service, and other county agencies. So this here is risk reduction. We eliminate man spraying in sensitive areas, places where we might have springs or we might have sensitive habitat, plant species we don't want to travel in and out of and bring noxious weed seeds into those plant species areas. We have the reduced need for wheeled vehicles, so they're not tracking, kind of like you can see in the picture at the bottom right. This was back to the job we did where we were having to travel through habitat that we could have sprayed around with something like a drone, but where a helicopter aircraft would have broadcast sprayed that whole area. So we have less exposure to the workforce also. We don't have a man out there doing it. We don't have a helicopter in the air and the dangers of helicopter. It's a very dangerous job to fly this type of spraying. We also don't have a spark arrestor at the fuel load level. We're not driving around in the field when it's spray season, which is a dry time of year. We don't have this exhaust and the hot vehicle in the field. And this just comes back to safety is a big deal here for the pilot, for the people, for fires, outbreaks, all these types of things, chemical safety, safety, safety.
Yeah, and Chris, no rattlesnakes.
Yeah, no rattlesnakes. Yes, that's a big deal for us around here.
So this is a concept project that we're working with a county on. It's a proof of concept project that was going to be used to see, just to gauge this project and process, which now we've kind of are past this almost, and this is going to be a full project the way it's looking. But where this started was a 7-mile long project. We use DEMs, which are digital elevation models for the site terrain. So we didn't use LiDAR on this. The plan was to use hyperspectral mapping to locate Scotch thistle, Medusa head rye in Dyer's Wood. We were planning on doing 1-day UAS application and the balance of the 7 miles traditional ground application. Do a post-treatment flight with hyperspectral to determine the mortality rate. And just to assess the time and that it took from one UAS to traditional ground survey. So conclusions, it's a technology-based workflow, precise identification of spray and no spray areas. It's measurable, it's quantifiable, it's repeatable, optimization, and risk mitigation. So using a UAS LiDAR for fuel load quantification, we identify terrain, fuel type, and biomass. Map using UAS LiDAR mapping for terrain and vegetation, and reporting an interface and georeference mapping that's integrated into agency GIS systems. So here's an example of how we would determine fuel load on a particular property. So this is actually a LiDAR, aerial LiDAR scan, and on the left, the higher of the two, the colored one on the left, you can see it's all kind of spiky. And what that is vegetation that the LiDAR picked up. And as it went down through the ground to get the true ground model, which is the bottom one, we're able to do a ground up DTM and then strip off all the vegetation above it. And the picture to the right is actually just a view looking at the scan from above. So with fuel load, I mean, we can do this with LiDAR, determine tons per acre, and if the type of species of plant is important, and that's where the hyperspectral would come in to determine that. And I think that's it.
If I could take a quick minute, Dan, to just kind of touch on the fuel load a little bit.
Yeah.
So in using this technology, if we had an area that we were wanting to expand fire breaks or that we thought had high fire assessment, this technology could be used to determine what areas might be better to have animals graze because of the species that were there, and what might be better to have someone like myself, a commercial applicator, come in and spray those areas or treat the noxious weeds that were there. And it also might determine what areas might be better to burn and have a fire, you know, to have a controlled burn in an area. And we're having this type of map and blueprint might make it easier for agencies to determine where they could do that at different times of the year and what their real fuel load threat was. You know, if there's so much fuel on one side of the road and, you know, so much fuel on the other, they might know they needed to make that fire break wider by using this technology.
That's great. Thank you. So are you ready for questions then?
Absolutely.
Okay. So if you have a question for Dan or Chris, please type them into your questions window in your control panel. And while you're doing that, I have a couple of questions. So I was talking to someone here at UNR who, you know, they're interested in using drones for natural resource management, and he was talking about standardization, and I'm wondering, is that something that people are talking about? Like, if there's going to be a bunch of different companies and agencies flying drones out there, is anyone talking about like standardization of flight speed and the camera settings, or is that just something that, say, the BLM was going to hire you to do that they would just have to specify that to you? How does that work?
Well, that's a good question. So the Department of the Interior has their Flight 107 unmanned vehicle regulations or procedures, and then every agency, it seems like, is developing their own under that are a bit different. The BLM, Fish and Wildlife, there's several other, like 5 or 6 agencies that have their own beneath that. So there's nothing as far as you call up and say you want this, you know, this is going to be, the deliverable is going to be different, and it's going to be different based upon each client, what they're requesting. Did that answer your question?
Yeah, thank you. All right, have you used this system in a forest below the canopy? I'm wondering about using this approach to evaluate post-fire areas for reforestation needs, or to evaluate the success of reforestation, live small trees versus dead small trees.
Yes and no. We've used it. We're working on a program with the U.S. Army Corps of Engineers currently, detecting unexploded ordnances. And we're required to, on some flights, to go through forest. Now, there is a difference between forests on the west coast to eastern Oregon, where you have eastern Oregon, the forests are pretty thin and you can fly through those fairly easily. It's maybe, I guess it'd be a case by case. We just need to look at it case by case.
We have had, Dan, some of the imagery we've seen with the LiDAR technology, even in a Malaysian jungle, though, could read all the way to the floor and determine between the ground floor and the canopy level.
Sure. No, absolutely. I was, for some reason, thinking that they wanted the sides of the trees for maybe the, you know, the width, diameter of the trees, you know, and species. Maybe I didn't know what they were looking for.
Okay, great, thank you. With surgical spot spraying, how close can the drones get to the ground?
Well, I mean, they can get right to the ground. We generally don't like to fly super close to the ground, and we've been usually, I think, in that 3-foot range is kind of where we've been hanging at. And the spot spraying apparatus does hang below the drone as well. So the farther away from the ground we are, the safer it is for our craft. So we can get as close as we have to.
Great, thanks. I have another question. So if you are, if someone wants to utilize this technology, you all get together and you map out where you're going to spray and not spray on these GIS maps. And then do you just go do it and then you come back you know, to the agency and share that information, or do the people in the agency like watch the video along with you while the person is flying? How do they, or is there like a video taken of the whole process so the agency can look at it after? How does that work?
No. So I mean, we can vary on what we give for deliverables, but typically We'll go out. I mean, obviously, when it's brand new technology, they're out there for a day or two just watching because they want to see it.
Mm-hmm.
But when we turn our deliverables in, it's in a report, you know, and with the GIS file where we sprayed, you know, here recording all the weather, temperature, everything, and then supply that in some type of a format, either being electronic or paper format in the report, so they know what we did. And then when we go back and fly, that's generally overlaid over the GIS map that was previously flown in Hyperspectral, and you can look at the mortality rate on that. So they'll have things in their hand in the office, electronic drawings and maps where they can be overlaid, and they can see, you know, what was actually done and how effective it was.
Great, thank you. All right, well, I don't see any further questions. If you're still typing, that's fine. I'll just go through my closing. So thank you all for your participation, and we would greatly appreciate it if you would take our 3-question survey that will appear after the webinar has ended. I will post the recording of this webinar on our Great Basin Fire Science YouTube channel this afternoon, and the link will be automatically sent to you through the GoToWebinar system tomorrow. If you have further questions regarding this or future webinars, please email or call me at any time. Again, thank you for attending, and thank you so much, Dan and Chris, for your presentation.
Thank you. Thanks, everyone.
Thank you. Have a great day.
All right, yeah, have a good day.